In this video, we'll look at the available built-in data types in C++ programming language. First thing, the internal representation of any quantity in computers is always binary. Everything is stored in binary format, whether it is a character or integer or real number or user-defined data type, everything is stored in the form of binary strings. The only interpretation makes it integer, real number, a character, etc. And it depends on the number of bytes and method used to access the memory. So same binary pattern or bit pattern can be interpreted as integer or a real number or a character string, etc. There are four basic built-in data types available in C++ programming language: integers, real numbers, characters, and booleans, which were added late to C++ programming language. By late, I mean in original edition of C++, there was no concept of boolean variable or boolean data type. Now, reserved keyword for integers in C++ is just like C language, it is int, int. It is int. And this usually indicates the natural size of an integer on the machine. And its variants are int, of course it is int, short, long, and long. All these are types of int only. And by default, all int, that is int, short, long, and long, they are signed. That is, they represent negative as well as positive, both types of numbers. But compilers are free to choose the size of an integer for their machines. So if you decide to design a compiler for C++ programming language, it is not necessary that you have to have the size of an int, short, long, or long, just like VC++ or Turbo C++ or G++, etc. But what I have seen is the size of an int is minimum size is 16 bits, that is 2 bytes. There is a restriction as far as size is concerned. The size of a short can never be greater than that of int. That is, short has to be of size less than or equal to size of int, which has to be less than or equal to size of long, and which has to be less than or equal to size of long. What sizes I have come across? They are Turbo C++ 3.0, which was nothing but a 16-bit compiler for 16-bit MS-DOS for 16-bit machines. Short, int, long, and long were of 2 bytes, 4 bytes, and 4 bytes respectively. It means sizes of short and int were same, and sizes of long and long were same. G++ for 32-bit compiler, which was for 32-bit Linux for 32-bit machines. Short was of 2 bytes, int was of 4 bytes, long was of 4 bytes, and long was of 8 bytes. Whereas in Visual C++ 6.0, which is here, 32, which was 32-bit compiler for 32-bit MS Windows, Microsoft Windows for 32-bit machines. The size of int short was 2 bytes, int 4 bytes, and long 4 bytes. Whereas long was found to be illegal. So it did not support long. G++ for 64-bit compiler for 64-bit Linux machines and 64-bit Linux for 64-bit machines, which are nowadays being used. I'm using G++. So short is of 2 bytes, int occupies 4 bytes, long occupies 4 bytes and long also occupies 8 bytes. So long and long both are of same size. Now there is a different way of declaring these short etc. With short int, long int, long int. These mean short, long and long respectively. It means whether you write short int or short, it is same. Similarly, long int or long, it is same. Long int or long, it is same. So generally, people tend to drop the int word when they want to say short int or long int or long int. Now, what are the ranges? By default, as I told you, all integers are signed. It means they represent both positive and negative numbers. If an integer or short or long is of 2 bytes, then we can represent minus 32,768 through plus 32,767, or from minus 2 to the power 15 through 2 to the power 15 minus 1. If it is of 4 bytes, this number through this number, or minus 2 to the power 31 through 2 to the power 31 minus 1. 4 bytes means 32 bits. So subtract 1. So minus 2 to the power 31 through 2 to the power 31 minus 1. If it is of 8 bytes, then this huge integer range. Or you can say minus 2 to the power 63 through 2 to the power 63 minus 1. Now there is a qualifier called unsigned. If it is used before any integer type, then it becomes capable of representing numbers 0 through some upper limit. So they do not represent sign and positive and negative both numbers. They represent then only positive numbers. So for 2 bytes, 0 through 65,535 or 0 through 2 to the power 16 minus 1. If it is of 4 bytes, then 0 through 2 to the power 32 minus 1. If it is of 8 bytes, 0 through this huge number, or 0 through 2 to the power 64 minus 1. Now, real numbers, there are two possible representations, fixed point and floating point. We'll see first fixed point. Using 2's complement, it is possible to represent numbers on both sides of 0 on number line. But there are few restrictions or problems with fixed point representation. Assume a fixed binary point. It is also possible to represent numbers with fractional component if you use binary points. So here it is not the decimal point. These are binary points. Here it is decimal point because we are representing. So this is also decimal point, sorry, here. Okay, the upper two are binary points, this one and this one. So by making use of fixed point, we can represent fractional part also. So here, if you remember, if you move towards left hand side, we represent the weights as 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3 and so on when you move towards left hand side. Similarly, if you move after binary point towards right hand side, the digit would be multiplied by 2 to the power minus 1, 2 to the power minus 2 and so on. So if I have written 10.01 in binary, it is nothing but it will be this 1 will be multiplied by 2 to the power 1, so result will be 2 here. This 0 is multiplied by 2 to the power 0, the result is 0. Add these two, this becomes integral part, that is 2. Then point. Here the 0 multiplied by 2 to the power minus 1, result is 0. Here 1 multiplied by 2 to the power minus 2, result is 0.25. Add these two, it is 0.25. So final decimal number represented is 2.25. But what is the limitation of this fixed point representation? The limitation is very large numbers or very small fractions cannot be represented. So to avoid this, scientific notation or floating point notation are used. C++ supports it. What is the advantage? Now, for example, if I have to write 456,000, 4,56,000, it can be represented as how 456 multiplied by 10 to the power 3. If I want to represent 0.456, it can be written as 456 multiplied by 10 to the power minus 3. What has been done here? The decimal point has been shifted to a convenient location. And exponent of 10, which is 3 here and minus 3 here, it is used to track this decimal point. And that is why floating point. It keeps on changing its position. It is something like we used to do in slide rules. In slide rules, if a quantity is multiplied by 10 power 1 or 10 power 2 or 10 power 3, the pointer would remain at the same location. You have to, you can say, guess or estimate whether it will be multiplied by 10 power 1 or 2 or 3 or so. Advantages: we can represent very large as well as very small numbers using only a few digits. This can be applied to binary numbers also. As in computers, the numbers are always stored in binary format. Generally, we can represent a number as here, written here, plus minus m multiplied by r to the power plus minus e. M is called mantissa or significant, r is radix or base, and e is exponent. So base is implicit and it is same for all numbers on a machine. That is why it is not stored separately. Base is assumed to be 2 in case of binary floating point. This representation can be stored in a binary word, that is 32 bits. So bit 0, so this 0, if it is the sign of the mantissa. Bits 1 through 8, these 8 bits, they are referred to as together, they are referred to as biased exponent. And bits 9 through 31, that is 32 bits, 9 through 31, 23 bits, 9 through 31, these bits represent the mantissa. So bit 0, sign of the mantissa, bits 9 through 31, mantissa, and bits 1 through 8, biased exponent. If sign bit is 0, mantissa is positive, else negative. In case of exponent, a fixed called the bias is subtracted from the field. It means a fixed quantity is subtracted from bits 1 through 8, whatever number they represent, to obtain the correct exponent value. Here, 8 bits of exponent result number 0 through 255. So if a bias of 128 is subtracted, correct values of exponent would be in the range minus 128 through plus 127. The base is assumed to be 2. Now generally real numbers are normalized. A normalized number is in the form plus minus 0.1 BBBBB and so on. This point is binary point. And B is either digit 0 or 1 in case of binary. Base is 2 and plus minus E is exponent. So the leftmost bit of the mantissa has to be always 1 for normalization. Hence it is unnecessary to store it, because we know that the leftmost significant bit, leftmost bit is going to be 1. And this is the way 23-bit mantissa field is used to store 24-bit mantissa field with values between 0.5 and 1.0. Now in such a 32-bit format, following floating point numbers can be represented. Negative numbers between these two quantities, minus 1 minus 2 to the power minus 24 multiplied by 2 to the power 127, and minus 0.5 multiplied by 2 to the power minus 128. Quite big range. Positive numbers between these two quantities, they can be represented. But remember, we are still representing 2 to the power 32 numbers, which comes out to be 4 GB if it is a bytes in memory. So 2 to the power 32 numbers only as the word size is still 32 bits. Approximately half of those numbers are negative and half of those numbers are positive, approximately. There is a difference of only one number of numbers. But the problem is, as we move near center of the number line, the exactly represented numbers come closer, and as we move farther away, the represented numbers spread farther apart. What does it mean? It means when you are towards the center of the number line, the number of numbers which can be exactly represented is more. When we move away from the center, the number of numbers which can be exactly represented is less. It means the number of numbers between two exactly represented numbers would be less. What does it mean? Now, for example, you have only, you want to represent 0.5. How do you represent 0.1? Binary. If you want to represent 0.25, how do you represent 0.01? Because 0.01 is 2 to the power minus 2, which is 1 divided by 4, which is 0.25. Now, if you want to represent any number between 0.5 and 0.25, how would you represent? You have to increase the number of bits. So, only those numbers can be represented exactly, which can be represented using sum of powers of 2. Only those numbers can be represented exactly. And that is why I always say, do not, last point, pay attention here, do not rely on results of floating point operations, as not all numbers can be represented exactly. Perhaps in the next video, I will give some examples and we'll see how floating point operations can be misleading. Results of floating point operations can be misleading. The following ranges are not representable in this format. This is referred to as negative underflow, negative numbers less than this number. Overflow. Negative underflow is negative numbers greater than this number. Positive underflow, positive numbers less than this. And positive underflow, this one. And all practical systems, they have a special bit pattern to represent zero value. Now, the reserved keyword for float or floating point number single precision in C++ is float. Floating point double precision, the reserved keyword is double, and long double for extended floating point. So precision of float has to be less than equal to double, which has to be less than equal to long double. And remember, precision offered by a compiler may be different. The precision offered is compiler dependent. These are the things which I have come across. 16-bit Turbo C++ 3.0, which was for MS-DOS. Float was of 4 bytes, double was of 8 bytes, and 10 bytes were used for long double. Visual C++ 6.0, which was a 32-bit for 32-bit MS Windows. So float was of 4 bytes, double was of 8 bytes, and long double was just like double, which is of 8 bytes. 32-bit G++ for Linux, float was of 4 bytes, double was of 8 bytes, and long double was of 12 bytes. And G++ for Linux, which is of course 64-bit for 64-bit machines, which are the modern machines, float is still of 4 bytes, double is of 8 bytes, long double is of 16 bytes. It means precision has improved drastically. Now, for sophisticated numerically oriented programs, IEEE, this is the third bullet you can see here, Institute of Electrical and Electronics Engineers, very popular society, IEEE. It developed in 1985 a standard named IEEE 754 standard for sophisticated numerically oriented programs. And just to make it independent of hardware, they made it independent of hardware to ensure the portability. It is widely accepted and adopted, and in most modern processors and coprocessors, this standard is used. The standard defines both single precision, that is 32-bit, and double precision, 64-bit formats. Both formats have bit 0 as sign bit, 32-bit format has 8 bits of exponent, whereas 64-bit format has 11 bits of exponent. And they, of course, base is assumed to be 2. This standard defines two extended formats also, single and double. So single extended, double extended. The extended formats have extra bits in both fields, that is mantissa field and exponent field for improving precision as well as the range. Here again, exit format is implementation dependent. Now see few things about IEEE 754 standard. Now you can see here, single precision, number of bits 32. In double precision, number of bits 64. Now single extended, number of bits has to be greater than or equal to 43, whereas in case of double extended, greater than or equal to 79 bits. Mantissa bits here are 23, here they are 52. Exponent bits here 8, here 11, here greater than equal to 11, and here greater than equal to 15. Now you can see here, exponent bias here is 127. Here 1023. Minimum exponent would be now minus 126, maximum would be minus 1222 minimum in case of double precision. Maximum exponent would be plus 127, in this case 1023, and so on. Now see how many fractions we can represent. 2 to the power 23, here 2 to the power 52, huge number. And decimal number range here for double precision C, 10 to the power minus 308 through 10 to the power plus 308, huge range. And wherever we have we find this cross, red cross, it means these things have not been specified by the standard. Now reserved keywords for characters. Another data type, built-in data type is character. So char is the reserved keyword in C++, just like C. And strictly speaking, it is nothing but a 1 byte integer. A character is 1 byte integer. Since it is 1 byte integer and it is signed by default, so it can hold values from minus 128 through plus 127. And as an integer, it can take part in any mathematical computation, single byte computation. In a next video, I will demonstrate it. But as character, it cannot take on any value below 0. Okay, so total number of numbers which you can represent a character says 0 through 127. So in one of the videos, I have already told you about control codes and etc., printable ASCII code and so on. By default, byte value of char is minimum is 0 and maximum is 127. And there is a qualifier called unsigned char. You can see unsigned. So if I write unsigned char, it becomes 8-bit ASCII, and codes are minimum value is 0 and maximum value is 255. Now it is not capable of representing negative integers, but it can represent numbers, positive integers 0 through 255. And the last reserved basic built-in data type is Boolean, which was added lately. So you will find that keyword bool was added quite lately, as I have written. Older C++ compilers like Turbo C++ 3.0, they did not support it. So if you declare a variable of type bool in case of Turbo C++ 3.0, which was designed in 1992, then it will say undefined or syntax error because it does not understand bool. So what we used to do is we used to use preprocessor directives hash define true for 1, hash define false for 0, etc. But Visual C++ 6.0 and G++ support bool. This is the keyword. A variable of type bool can be assigned a value 0 or false or 1 or true. But remember, since they are internally represented as 0 or 1, as the case may be, they can also take part in most of the mathematical computations. In the next video, I will demonstrate this. That is all in this video. Thanks for watching.